Hey everyone, welcome back. Welcome to Unit 10. This is Lesson 4 in the series titled Neutralization Reactions. So in the last video, we covered pH scale, indicators, and how the different colors related to what the pH was. And today we're going to focus on neutralization reactions. And so your first thought may be, neutralization kind of looks like neutral. It's going to have to do something with the pH of 7. And so that's a good initial thought to have. So in neutralization reactions, it's a mix with an acid and a base. And so generally what happens when that happens is, you have your acid, you have your base. When they react with each other, they form water and a salt. And so water, remember, has that pH of 7, which is neutral. And so that's kind of where the term neutralization reaction comes into play. Now, with this, neutralization is a double replacement reaction, meaning everybody gets a new partner. So when you break it up, let me clear this up a little bit. When you break this apart, your acids become H and then everything else. Your base is OH and everything else. Your outside people go with your outside people. Your inside goes with your inside. And so if everybody gets a new partner, that is double replacement. But one of the most important things, and again, the general formula for a neutralization reaction, is your acid plus a base will give you salt and water. So that's how it works very basically. So with this, neutralization happens, again, when you have that pH of 7. So you have, that water, which is neutral, and that salt, which is neutral. And so again, when we talked about pH scale, if something is neutral, that means the amount of H plus ions is the same as the amount of OH ions. Remember, the more H plus ions you have, the more acidic you are, the lower the pH. The more OH you have, the higher the pH, the more basic you are. So when you're neutral, both those things equal to each other. Now, you don't always get a completely neutral solution. And so if you have a strong acid and a strong base, you get something that's 7, perfectly neutral. Weak acid, weak base, again, you get something perfectly neutral. Now, when you have a strong acid and a weak base, because the acid is a little bit stronger, your final pH of your neutralization reaction will be a little bit less than 7. It will be a little bit acidic. And the exact opposite, if you have a weak acid and a strong base, when it's neutralized, it's not a perfect 7. It will be a little bit higher and a little bit more basic. But when we do these neutralization reactions, we want to make sure our equation is balanced. And so there's a cool way, like maybe an easier way, to balance these types of reactions. So let's just jump into it. For the most part, you'll be given, these two things, an acid and a base, and say, okay, cool, what are the products? And so we have MgOH and we have HCl. So I'm going to write it like this. We have MgOH2, that is our base, plus our HCl. And you'll see why I'm writing this like that in a second. And it's asking for what happens when the neutralization happens. So when they're in, these are in aqueous solutions, you have these two things, and they dissociate into their ions. So we get, whenever you have a base, you're going to break it in half. You have OH, and then everything else. And your acid, you're going to break it up, so you have H and everything else. And so your outside people are going to go together, and your inside people are going to go together. Now, with this, I like to write water. We know water is H2O, but I'm going to write it like this. HOH. That's still, H2O. But here it's easier to see where the O's and where the OH is and where the H is coming from. So this red H comes from there. This OH comes from there. So now we have that. And now we have to make a compound with Mg and Cl. Now, we have Mg and Cl. We can't just throw those two together. We have to think all the way back to like unit 3 when we're talking about making ionic compounds. And your charge of your overall compound has to be 0. So if you look at your periodic table, magnesium has that +2 charge, chlorine has that -1 charge. So you crisscross it to get MgCl2. So as of right now, our formula stands like this. So I'm going to write it weird so we get the different colors. This. And we have that. Okay. But the problem is this is not a balanced equation. We don't have the same number of each thing on either side. So what you can do, and here's the kind of new way of balancing, and honestly, I've only seen it work on neutralization reactions, but have fun with it. And this is why, I like color coding it. So we have one OH group on the right side, but on the left, we have two OH groups, and we need to make sure that's equal. So we'll put a big 2 in front of that. So now we have two OH groups to match this. Fantastic. But in doing that, remember this big number or that coefficient affects the entire compound. So now we have 2 of those red H's on the right side. But the left side only has 1 red H, so we put that there. And now we have a balanced reaction because we have 1 Mg here, 1 there. We have 2 OHs, we have 2 OHs. We have 2H, 2H, 2Cl, and 2Cl, and that is your balanced reaction. So again, there's a lot of kind of callbacks to previous units, but doing it step by step by step definitely helps, and writing it as HOH helps. So let's do one more together. This one says, write the neutralization reaction between phosphoric acid and sodium hydroxide. Now you might be thinking, how the heck am I supposed to know what these are? Do not panic. That is what table L and table K are for. So phosphoric acid is going to be H3 PO4. Again, that comes straight from the reference table, table K and table L. And then we have sodium hydroxide, which is NaOH. And so it's asking, well, what happens? So again, we're going to break it up. So we get our H and everything else for the acid, and then for the base, the OH and everything else. Again, outside with outside, inside with inside, that's that double replacement. So we're going to get HOH, that's again our water. We're just writing it a little bit differently. And then we have Na and we have PO4. Remember, metals come first and then nonmetals. So we can't just throw these two things together. We have to check the charges. So Na is in group 1 and has that +1 charge. PO4 has a -3 charge, and we know that because it's on table E, the table of polyatomic ions. So now that we have that, we can crisscross to get Na3PO4. And so now if we were to rewrite this, we have Na3PO4, add in the H, add in our OHs. That's a neutralization reaction. But again, it's not balanced. And so what we're going to do, again, what the easiest thing to do is, with these types of neutralization reactions, is balance the O's and the OHs. You can definitely go back to the old way of balancing when we did it, in unit 5. But I like this method for here. So we have 3 red H's on the left, 1 red H on the right. So let's go ahead and put a big 3 there. Cool. Now that means we also have 3 blue OHs. We have 1 blue OH here. Let's go ahead and put that 3 there. Now we're balanced, just so you believe me. 3 red H's, 3 red H's. PO4, we got PO4. We got 3 NAs, we got 3 NAs. We have 3 blue OHs, 3 blue OHs. There is your perfectly balanced neutralization reaction. So, with that being said, that is it. On the next time, or the next video, we're going to cover the last topic in this unit, with it being titration. Until then, have a wonderful